In this video, we're going to look at a concept called co-universality. And as with any time we see co in front of a term in category theory, we're almost always talking about the dual of the concept that we're looking at. So in this case, the concept that we're looking at is universality, and we'll review that in a second here. And so co-universality is going to refer to the dual of universality. And what is the dual? Well, the dual is when we flip all of the morphisms in the pattern that we're looking at. So let's first review what the pattern for universality looks like, and then let's look at what it looks like to flip all of the morphisms in that pattern. So when we have a functor f going from a category D into a category C, we say that the pair UC, where U is an object in D and UC is a morphism in the category C going from some arbitrary object C into F of U, is universal for that object C and the functor F if for any D in D, any arbitrary object in D, and any morphism F going from C into F of D, there exists a unique morphism, tau of F, going from U into D in the category D. So here we have that tau of F goes from U into D, such that the image of that tau of F under the functor F will allow this diagram here to commute. So that is that F will be equal to F tau of F after UC, and that's the equation that we have right there. So now, to get the definition of co-universality over here, let's take this diagram, flip all of the morphisms, and then use the new diagram that we generate down here to sort of reverse engineer the definition of co-universality. So in this case, we had a functor f going from a category D into a category C. And in this case, you'll see that we've flipped the direction of f. This time we're going from C into D. But that's not because we're looking at the dual concept. You don't need to flip the functors when you're looking at the dual of a concept. The only reason I've done that is because I want to make this terminology a little simpler for later on. So we've flipped the functor f here, but that's not because we're looking at co-universality. It's just because I want to make the terminology easier. The morphisms, on the other hand, have all been flipped from this diagram, and that is because we're looking at the dual of this concept. So we always have to flip all of the morphisms in all of the categories, and that's what we've done here. So you can see that before we had a morphism, tau of f, going from U into D in D. And so in this case, the morphism tau of f is going to go from our arbitrary C this time, since we're in the category C, into our universal object U. So tau of f goes from C into U, which means that f tau of f has to go from f of C into f of U. This time, our arbitrary object in D is going to be called D. And so for any arbitrary morphism f going from f of C into D, so here we were coming out of our arbitrary object C, this time we're going into our arbitrary object D. And we've also flipped, of course, the universal morphism up here. So what used to be UC going from arbitrary object C into f of U has now become morphism UD going from f of U into arbitrary D. So now that we've generated our diagram down here, let's use that to generate our definition for co-universality. So as I mentioned in the video on universality, a lot of times in category theory, it's much easier to memorize these sort of patterns as diagrams like this, and then use that to write down the definition. You sort of just look, okay, what's commuting, which morphisms are where, in what category, and then you can write out the definition like this, rather than trying to remember this sort of terse definition that does make sense once you have the context of this diagram, but might be hard to just remember on its own like that. So let's do that here. So in this case, we said that UC was universal for CF. So in this case, we're going to say that UD is co-universal for D and F this time. If, while here we had for any arbitrary D in the category D, so here we're going to say for any arbitrary C in the category C, and while this morphism F was going from C into F of D, but this time we said that our arbitrary morphism F was going from F of C into D. There exists a unique tau of F, which in this case went from U into D, and in our case goes from C into U, such that this triangle here commutes. That is, F is equal to U of D after F tau of F. So you can see how these equations here are quite similar, but it's the dual of that concept. So now let's use this definition that we've generated for couniversality, and let's look at an example. And specifically, let's see how the categorical product can be thought of as co-universal for the diagonal functor. And so we need to recall some definitions. What is the categorical product? What is the diagonal functor? And when we do, we'll be able to prove that it's actually an example of this concept of co-universality. First, let's recall the definition of the categorical product. So if A and B are two objects in a category C, then we can call the triple A cross B row A row B, where A cross B is an object in the category C, some object A cross B in C. Row A is a morphism going from that A cross B into A, and row B goes from A cross B into B, where we call row A and row B the projection into A and the projection into B, respectively. So that triple together is called the categorical product of A and B in the category C. If for any object C in the category C, when we have a morphism going from C to A and from C to B, which we might call F of A and F of B respectively, then there exists a unique morphism, theta, here going from C into A cross B, such that both of these halves of this diagram commute. That is, F of A is equal to theta and then rho of A after theta, and F of B is equal to theta and then rho of B, F of B is equal to rho B after theta. Next, let's look at the definition of the diagonal functor. And first, let's remind ourselves the definition of the product category of two categories. So say that C and D are two categories. Then the product category, C cross D, consists of objects, which are ordered pairs of the objects in C and D on the left and right respectively. So all of the pairs CD, where C is in C, and D is in D, where C and D are objects, of course. And the home set between any two objects in C cross D. So if we have a pair CD and a pair C prime D prime, then the home set between those two will consist of pairs of morphisms. So just as we have pairs of objects, we have ordered pairs of morphisms, where the one on the left goes between the two objects on the left sides, and the one on the right goes between the two objects on the right side. So we have F going from C to C prime and G going from D to D prime. Composition is defined as expected, so FG after HI is equal to F after H paired with G after I. We can use that to define the diagonal functor, which we'll call delta. So delta goes from a category C into the product category of C with itself, C cross C, and it simply sends any object C in C to the pair C, C, which is of course in C cross C, and it sends the morphism F from C to C prime to the pair F, F. So it just basically copies itself twice, either as an object or as a morphism. With those definitions in place, we can now look at our example of couniversality. So we're going to see that the categorical product is actually co-universal for the diagonal functor. So we just defined the categorical product and the diagonal functor, and we'll now use those definitions to show that this is an example of co-universality. So how do we go about proving this? Well, obviously this is a pretty abstract statement, so we're going to need to break it down a little bit more. And so one exercise that would be good would be to try to pause the video here and first draw out this statement as a diagram of co-universality. So we saw earlier in the video what a co-universality pattern looks like. So try to draw that out for this specific case, and then use that diagram to write out the full definition of what co-universality is going to look like in this case. So we're going to go ahead and do that, but as an exercise, you could pause the video here and try to draw it out and then write out the definition based on the first part of the video. So here we've drawn back out the pattern and we've just removed the labels for our co-universality diagram. So we're using the functor delta, the diagonal functor. And so now we want to basically put the labels on each of the objects and the morphisms in this diagram. What would it mean to say that the categorical product is co-universal for this diagonal functor? Well, we know that the object part, the first half of the pair in the co-universal, is the object in our category C on the left here. And we know that the categorical product is found here. So obviously the object part of the co-universal is going to have to be the object part of the categorical product here. So we'll label this as A cross B. And then we know that we need to be coming from any arbitrary object C in C. So we can label this as C. Well, that means that this here is the image of A cross B under delta. So what does that give us? Well, that gives us A cross B on the left and on the right, where the right-hand side is the product category of C with itself, C cross C. And so we can label this as C, C, the image of C under delta. We still have the projection morphisms from the categorical product of A and B here, which we know will obviously have to line up with the morphism part of the co-universal. So in this case, we know that UD, which was the generalized name for it, in this case will actually be the pair row A, row B, the projection from A cross B into A and the projection from A cross B into B. But then the question is, what do we label this? Well, we know that row A has to go from A cross B into A. It's the projection into A, so obviously it goes into A. And same for B. We know that row of B has to go from A cross B into B. So this has to be the ordered pair AB in C cross C. Finally, in the generalized diagram, this morphism was just an arbitrary morphism F, which in this case will be a pair of morphisms in C, which we might call F1 and F2, going from CC to AB. Now that we've drawn the situation out down here, let's write it out as a little bit more of an exact definition. So when we say that the categorical product is co-universal for the diagonal functor, what we're really saying is that the pair A cross B and the morphism UD, which in this case is the pair row A, row B, the two projections of the categorical product, is co-universal for, well, this is going to be the pair here, the ordered pair A, B, as well as delta, our diagonal functor. So this is effectively the statement we're trying to prove. And so what do we need to do in order to prove that? Well, what is the definition of co-universality? We can get it from here again. We basically need to say that for any C in C over here, and for any arbitrary morphism here, which in this case is a pair of morphisms, F1, F2, which go from the pair C cross C into the pair AB, we must have a unique tau of F over here, such that the image, which in this case is going to be tau of F, allows this diagram to commute, which effectively means that there exists a unique tau of F going from C into A cross B, again in the category C, such that this diagram commutes, that is F1, F2 is equal to this followed by this, that is row A, row B, after tau F, tau F. So we have the statement that we need to prove here. And so in order to do that, it needs to be true for all C and C and for all F1, F2. So we start by letting C be an object of C and F1, F2 going from CC into AB. Well, we need to establish there exists a unique condition. And we've said before in the past that every time we need to prove there exists a unique condition, we actually need to prove two things. We need to prove the existence criteria and we need to prove the uniqueness criteria. So first, let's establish that there is this tau of F that allows the diagram to commute on the other side. So notice that if F1, F2 goes from CC to AB, then by the definition of the product of categories, we have that F1 must go from C to A because the first morphism goes between the objects on the left and the second morphism goes between the objects on the right. So we get that F1 must go from C into A, and similarly F2 must go from C into B. But then, if you recall the definition of the categorical product, we have a morphism, one going from C into A and one going from C into B. So we've satisfied the conditions of the definition of the categorical product, which means we must have some unique mediating morphism theta going down the middle of that diagram in the categorical product, which goes from C into A cross B, such that first, row A after theta is equal to F1, and row B after theta is equal to F2. Which means that we can say that F1, F2 is equal to, well, we can replace F1 with row A after theta and F2 by row B after theta, which is equal to, well, we can split out these compositions to give us row A, row B after theta, theta. But what do we notice then? Well, we've satisfied the existence criteria up here. If we replace tau f by theta, this unique mediating morphism created by the categorical product, or not created, but guaranteed to exist by the categorical product of A cross B in the category C, then this equation is satisfied, as we see here. F1, F2 is equal to row A, row B after theta, theta, where tau of f is replaced by theta. The only thing left to show is that tau of f is unique in this case, that only theta will satisfy this property, but that's also given to us by this categorical product, because this mediating morphism theta is the only morphism that makes these two equations true, and therefore this chain of reasoning can only apply if we use theta in this case. So we have that there exists a tau of f, namely theta, and it's unique. So we can call that QED. We have proved that the categorical product of A and B, together with the projections into A and B respectively, forms a co-universal for the ordered pair AB in the product category C cross C and the diagonal functor delta.